as you know, talk about ZK-Snarks. And so I think like I'm trying to keep these feeling like fairly casual. So his talk will take up to 45 minutes with questions after. But if you have questions during his talk as well, please feel free to ask it. It's nice if it feels like a conversation and not just him talking at blank screens with people muted and cameras off, if we can handle the bandwidth. Thanks all for coming. Over to you, Christian.
Thanks, John, and thanks for organizing the roundtable. I think it's a really good initiative. So I'm gonna start the presentation here. Basically, I'm gonna talk about ZkSnarks, and the idea here is that most expositions on ZkSnarks I've seen has been more like starting with this is how the math works, and you start with elliptic curve, bilinear pairings, all these things, which is interesting, but it's kind of daunting, and it doesn't really help you wrap your head around how you would use this in smart contracts, etc. if you're a developer. So the outline of my talk is basically going to be introduce ZkSnarks from a kind of high-level functional perspective, like how do they work, how do I use them, what can I get out of it. Not so much math, more about practical examples, and then I'm going to give an example of how to use ZkSnarks in an Ethereum smart contract, how that may look like. I don't know exactly how it will look like, because I haven't been that involved in the actual implementation, but this is what we can expect. And if you read my the blog post that I put out, then this will follow that pretty well. So if you had any questions when you read that, then you can ask me now. Anyway, what is a ZK-Snark, or rather, what is a zero knowledge proof? So it's the following. Let's see. Sorry, I need to fix the screen here so I can see it. Zoom keeps putting the window on top of all the text. Okay, let me do this.
If Zoom is maximized, it just gets in the way of everything.
Yeah. Maybe I can like.
We can still see your screen right now.
Yeah, I know. I just want to see it myself. Let me see. If I hide Zoom. Oh,
if you do like Command Control F, it should make Zoom be not full screen.
Okay. I don't think it's full screen, but it just keeps putting itself on top of everything. Okay, this works. Anyway, what is a zero knowledge proof? The idea is that you have one person is a prover. They want to prove to some other person, the verifier, that they have knowledge of a particular secret that has some properties, and they want to prove this without disclosing the secret itself. Okay, so this could be useful. So what do we mean by certain properties here? We usually express this using a program, or it's common in the literature to call it a circuit. And so this we can denote by this function CXW. The input to the function is you have a secret, it's called W, also known as a witness, and you have a public input X. And the output of this function is true or false. So a simple example that I'm going to use in the upcoming example is this, where you have a function, it has a public X, a secret W, and it returns true if the hash of the secret is equal to the public output. So in this example, it's kind of like we would want to prove that we know a value that hashes to another value that's public. So that's the 10,000 foot view. So what is the definition here? So a ZK-Snark consists of 3 algorithms. So first is the generator, then we have the prover, and then we have the verifier. And it follows the previous slide. So what's the generator? So we have a circuit or a program. So remember this encompasses the properties that you want. And when you run the generator, you create a proving key and a verification key. These are public, you can share them with anyone, and they will be used when creating proofs. So you see one of the inputs here is this lambda, and this is randomly generated, and this is what's known as the toxic waste that everyone's talking about in when they talk about Zcash. And Zcash has this big ceremony that to allow them to create this lambda in such a way that no one knew about it and no one saved it anywhere. So we can come back to that, but right now it's just a random parameter that's designed to create those proving keys and verification keys. Okay, so now if you are a person who knows the secret with these properties, so you know a secret such that this program is true, then you can run the prover, the proving algorithm, to generate a proof. So we see that here, we call it PRF or whatever. And so P takes as input the proving key. That basically says, okay, we're going to prove things about this particular program. X is the public input. W is the secret. So if you know W, you can create this proof. Okay, now we can use the third algorithm, the verifier, to verify the proof is correct. So how do you do that? Well, you need the verification key. This is all public. You need the public input and then the proof. You plug that into the verifier, and the verifier will return true if the proof is correct. So you've seen here that the proof, and another thing here, another property of the proof is that it doesn't reveal the secret W.
I forget, what is X? W is the secret. What's X?
X is the public input.
Okay.
So you have the circuit. It has a public input. It has a secret input, and basically you can think of X as kind of parameters, so that you don't have to run the generator every time. All right. We're going to come back to X in an example. But anyway, so the proof proves that you know the secret, but it doesn't reveal the secret. So that's the magic here. And this lambda is a little sensitive, because if you know this lambda parameter, then you can create a proof such that the verifier will claim it is correct, but you can do that without knowing the secret. So that's why everyone's so sensitive about it, because in Zcash, that means that you can create proofs that you send money, but you actually didn't have the money, and so it's really bad if someone knows that. Okay, so that's kind of the definition, and here's an example of how this can work in practice. So suppose Alice knows a secret, we call it S, and it has a specific hash H. So you can imagine the hash might be in a blockchain or something. Everyone knows it, but only Alice knows the secret. She would want to prove to Bob that she knows the secret, but she doesn't want to reveal the secret itself. So, I mean, revealing the secret would prove that she has it, but she doesn't want to do that. So how do we use ZkSnarks to solve this problem? What happens is Bob can run the generator, and he would generate the keys, the proving key and the verification key. He shares those with Alice. Alice uses the proving key to create a proof. So she plugs in the proving key, the hash, and the secret. The output of that is a proof, and she shares the proof with Bob. Bob uses the verification key, the public hash, and the proof. It spits out correct, and so that's how he knows that Alice knew the pre-image of this hash without actually revealing that secret value. So you see here in this case, when we have Alice needing to prove something to Bob, it doesn't actually matter if Bob knows this lambda parameter, because the only thing that matters is that Alice doesn't know it. If Alice finds out, then she can fake proofs, but here it doesn't really matter if Bob knows this value. So sometimes you have these kinds of situations where you don't have to have an elaborate, you might not have to have an elaborate ceremony for this lambda, because it might not matter that one person knows it. So the kind of cool stuff that's happening now is that, let me back up. Like, are there any other questions here about?
I have a question.
Yeah.
Okay, so in Zcash, for example, there's only, correct me if I'm wrong, there's only one like circuit. There's only one program, which is like the sending money circuit. So yes. Is it the case that the generator function in Zcash would have only had to have been run once, and everyone uses the same proof and verification keys?
Yes, very good question. It only had to run once, and this was the whole big ceremony where Peter Todd was in a RV out in the desert doing some shit, and the output of all this was this proving key and verification key, and now everyone can just use them if they trust that the people did it correctly.
Gotcha. Cool.
And that would be the case for I think a lot of the things you will see on Ethereum also. You need one setup phase for the generator, and then you can just use those keys. This example is more kind of like, you could also have a situation where maybe you just need to do a one-time thing between two people. So that thing exists also. But in Zcash, you just need one generate that thing well. Any other questions?
The parameter X, would that also make sense to call like a challenge or a question?
Maybe.
I mean, I guess like that's how I'm thinking of something from another sort of explanation that I've read where it's kind of Bob challenges Alice by saying, like asking a question that she can't anticipate, and then she takes that and proves that she has the
So I think this is more when you're talking about what's called interactive zero knowledge proofs.
Yeah.
So those are basically like Alice wants to prove she knows a secret. So what Bob does is that he asks questions about the secret, and usually it's like if Alice was trying to fool Bob, she might have like if he asks one question, she might have like a 50-50 chance of answering correct. But if he then asks 20 questions, then the probability is very low for her to answer correctly every time. So that's kind of the more traditional interactive zero knowledge proofs, where you have this back and forth. Whereas what the ZkSnark is that it's non-interactive. So the N in snark is actually stands for non-interactive. And the good thing there is that the proof is just like a blob, and Bob can just verify that blob. But yeah, good question. Any other?
Christian, further to that question around probabilities from the interactive proofs where you tend towards zero, does that, how do we think about the probabilities of these non-interactive proofs?
So I'm not 100% sure, but I believe basically what we're proving here is something along the lines of knowledge of a value that causes a certain polynomial to evaluate to zero, and there is like only one in, let's say, 2 to the 256 or 2 to the 128 values will cause this to happen. And so you can say that it's kind of probabilistic, but it's more like randomly generating a digital signature and have that validate. Right? It's possible, but it's very unlikely.
Thanks.
Any other questions?
Why are there two amounts in Zcash? Was that something separate?
So my next endeavor is actually trying to understand what exactly this circuit of Zcash does. So I don't actually know. I mean, it's something about membership in a certain Merkle tree. Like maybe someone else knows this better. But yeah, I'm not fully familiar with Zcash, to be honest.
I get so taking it back to this X thing parameter. I think I'm just trying to sort of like understand it in a more sort of like relational, like conversational aspect, sort of. So like with the interactive, we have Bob saying, okay, well, if I ask you this, can you answer it? In this case, is it more like Alice is saying Alice is proposing X and proving and like through that, like where does X come from and how is it chosen?
Yeah, so I think you can think about it you can think about this actually without having X. So let's say X is not there. So you have a function that just takes in a secret and spits out true or false.
Okay,
Right?
and so yeah, and then Bob or Alice knows. No, sorry, Bob is the one who doesn't know the secret. So Bob knows the program then.
Yes, Bob knows the program. Okay. Everyone knows the program, and you can think of X as like just parameters that goes into the program. So if you know the program and you know X, then you know all the parameters. And basically, you phrase it with the X so that you don't have to run this generator every time.
Yeah,
that's a way to think about it.
Okay, so everybody trusts the program, and if somebody comes along and they can make the program evaluate to true, then they've shown that they know this information.
Yes, exactly. And so in our case here with the hashes, the program is this, that, you know, the hash of this equals that. So everyone knows the program, everyone knows the hash, and if someone creates a valid proof, then you can know that they know the secret. Okay, awesome questions. Any other takers? Because I have a little bit more. Okay, cool. Yeah, so ZkSnarks on Ethereum is what everyone's excited about. Support will hopefully be added in the Metropolis hard fork. What does this mean, ZkSnarks on Ethereum? Well, it means that the verification function, so the thing that we use to verify these proofs, that will be callable as a function. Not quite an opcode, but more like a pre-compiled contract. So you can call that from a smart contract to verify proofs inside smart contracts. So you can do things like, if the proof is correct, then do X, Y, Z. So here again, we in like a blockchain setting, we need to trust the people who generate the proving and verification keys. Otherwise, if they are malicious, they can create fake proofs. That's not good. So it's likely, from what I've heard, again, I need to investigate more, but we should be able to reuse the proving key and verification key that were generated in the Zcash ceremony. So that would be awesome, because then it's like, okay, you know, we trust Suku and Peter Todd and those guys, so we can just use what they have. So here is an example, or any other questions on that? So here is an example of how you can use ZkSnarks in an Ethereum smart contract. So I call this confidential tokens, and the idea is we want a standard token contracts, but instead of balances being integers where you can see everything, the balances are hashes. So only the hashes are stored on the blockchain, and in order to send tokens, so in order to update the balances, we're gonna use ZkSnarks, and we're not masking the sender or receiver. So if I send something to John, you'll be able to see that my address sent to John's address, but you won't be able to see how much, and you won't be able to see what our balances are. So what would the ZkSnarks be proving in this case? Like, what are the circuits what we need to prove is that the value we sent is smaller than the balance of the sender. We need to check that the balances are updated correctly, so that the sender has his balance lowered and the receiver has his balance increased. And we have to prove that the hashes match the values sent and the updated values. So we start with some hashes, we're going to end with some hashes, and we need to show that everything is, that these are updated correctly. So again, here's the description of the circuit for the sender. So the public input here would be the hash of the value that we're sending. Also the hash of the value we're sending, the hash of the starting balance, and the hash of the ending balance. So I should make this more clear that these are all hashes, right? So that's the public one. Everyone sees the hashes. That's fine. The secret input is the actual value sent and the actual starting balance. And the program returns true if, again, the value sent is less than the starting balance, and all the hashes match. So the hashes that are public need to match the actual balances. And we have another circuit for the receiver. And again, we have the as public input is the hash of the value sent, the hash of starting balance, the hash of the ending balance. The secret is the value sent and the starting balance. And it would return true if the hashes all match. So basically it means the hash of the value is the corresponding public input, the hash of the starting balance is the corresponding input, and the hash of the starting balance plus the value matches the ending, the hash of the ending balance that we have as a public input.
So like, is it the case that, you know, out of band to whatever protocol, like secretly the sender has to share the value sent and the starting balance with the receiver? Is it like unrecoverable to the receiver otherwise?
Very, very good questions. Yes. Well, okay.
Because I've wondered about in Zcash, like if somebody sends me a secret transaction, how do I actually know? So maybe this is getting at that.
Yes, exactly. No, that's a very good question. There has to be an out-of-band communication with the receiver saying, hey, I'm about to send you this much. And once they know that, they'll, I have actually some funny pictures. But yes, you're absolutely right. There needs to be an out-of-band communication here. So this is basically an overview of how this would work. So we have this token contract. We have Alice has some hash of her balance. Bob has some hash of his balance. A trusted third party, here is Santa Claus, which everyone trusts. He would generate these verification keys and proving keys. And in this case, it's 2 pairs. So that only happens once. And then, you know, these are published on some website or whatever, and everyone can just use them. So how does it work now if Alice wants to send some tokens to Bob? So here is what Mike was talking about. In this out-of-band communication, like an email or whatever, Alice says, hey, I want to send you 100 tokens. And it looks really weird now, but that's basically, if you just say 100 tokens, someone can guess and be like, hey, I wonder if she says 100 tokens, and then they can reverse engineer that hash. And so this is a way to kind of put in some entropy in the value, so that it's hard to reverse the hash. So she wants to send 100 tokens. So what they do, both of them, is to create a proof each. So the Alice first, she uses the sender proving key. She uses her starting hash. So that's this OXABCD there. She used the hash of this value, the 100 tokens, and then the ending hash, which is her starting balance minus the value. And then she puts in her secrets, which is the starting balance and the value. So she runs that algorithm. The receiver also runs their proof. So they use the proving key of the receiver. Again, they use the hash of the starting balance, the hash of the value, 100 tokens, and the hash of the ending balance. And as secret inputs, he would use his starting balance and the value here. So both of them create proofs, and now they can basically call a function in the contract and post. So Alice posts her proof. She posts her ending balance and the hash of the value. Bob, again, he posts the proof. He posts the hash of his balance after the value has been sent, and the hash of the value. So notice here that everything here is public, but it doesn't reveal anything about the balances of Alice and Bob, or anything about the how much value was sent. And the smart contract runs the verification algorithm. So it uses the verification key, it uses the current balance hash, it uses what Alice reported as her the hash after the value, the hash of the value, and then the proof. And so the smart contract checks both of these proofs, and after it checks the proofs, it will, if both of them are correct, it will update the hashes. So the state tree only has the hashes, and the transaction only contains hashes and proofs. So no data is actually revealed here. Thank you.
Thank you, Christian.
That's it. So, yeah, please ask questions.
So I'm sure you've thought about, because I immediately thought about, it would be cool if, like say in Uport, for example, I could provide some proof that I have a certain attestation without revealing who I am. Like I could, reveal that I'm licensed to party without revealing my actual identity. So how would that work in Uport? Like at a high level?
Yeah, no, that's a very good question. So basically, the way things like that would work would be, I can use a different, let's say I use a different key to identify myself when I talk to you, and when I talk to John, or when I talk to anyone else. And so when you just see, and you can make an attestation, or you can make an attestation that, hey, this the person that has this identifier is licensed to party. And if I show that to John, he wouldn't necessarily know that it's me, right? But maybe I want to reveal to John that, and I might have an identifier that I'm using with him that's not tied to my personal information as well, or to my core identity. But when you're, but the way that the system works right now is, if I want to link those two together, I basically have to do something like sign a statement with my master key that contains both of those attestations, and that would link both of them back to my main identity.
Gotcha. So well, go on. Sorry.
But using a zero knowledge proof, you can say something like, there exists basically a U-port contract that has control over both of these keys, and so that's a way to link these two, and prove that they. So let's say you check my passport and verify that I'm over 18, and John is a bar, and you can use this to prove that, okay, there exists some identity, like real world identity, with an attestation from a bank or whatever, and it has an attestation by Mike, and this same identity is controlling the key that I'm using for John, but it's not. It doesn't reveal, the core identity there. So that's, I haven't thought through all the details there, but it's definitely something that's that we've been discussing.
Cool. So just to make sure I understand the general workflow of these things. So in principle, to implement this, a new generator function would have to be written, and that could be run once off chain to generate proving and verification keys. A verification function would have to exist on chain. The proving functions could run off chain.
Yes, exactly. Okay. So the verification function is the only thing that's on chain. Proving and generating would be done off chain.
Cool. Very cool.
That's the idea.
Hey, Christian.
Yeah.
So I guess maybe just to follow up on what Mike was saying around the verification function. That would be, it would only need to be one of those, and it would work with all circuits, so to speak.
Yes, exactly. Because what it is this verification key that actually determines which circuit we're verifying. So you only need one generic verification function.
And is that the same for the generator function? And does the generator function work across any circuit, or are the circuits limited in a certain way to be of a certain type?
So yes, theoretically it works for any circuit, but there is a large cost in computational power to run the circuit and to run the proofs. To run the generator and to run the proofs for a specific circuit. If you have a very small circuit, then it's not that costly to run the the generator and the proving function. But if you have a very elaborate one, it can actually be prohibitively expensive. And so this is where you need to be, this is where it gets a little tricky. So for instance, in Zcash, like the one of the big breakthroughs there was actually to create a circuit that was where you were actually able to create a proof in a reasonable amount of time.
So Chris,
yeah.
I'm just trying to see if you can help me quantify this in my head at a very high level. In the talk I gave in Taiwan earlier this week, he talked about zero knowledge proofs in Ethereum, and he just put a number on it. Obviously, Ethereum company. He said it's going to cost something like $1 million gas to do this knowledge proof work. My question to you is, where's the $1 million gas fit that Vitalik talked about in rough order of magnitude to the two ends of the spectrum you were just describing? That could get crazy. What's the more normal one that Vitalik might have been meaning?
I'm not.
Well, he must have been talking about the verification functions, right? Because only those have to run on chain. It would be my guess. I actually haven't seen his talk.
Yeah, I haven't seen that either. But I'm guessing that would be the verification function. And I'm thinking the verification function might also depend on what type of circuits that you are verifying. But anyway, that was a good data point. I hadn't heard that data point.
I can help you find that.
It kind of shows that it's, this is something that straddles the line of like almost being unfeasible to run on chain.
Yeah, that's what I thought. I thought it was real useful. So it will be good to get our heads around it. Listen, what you've done today has helped me immensely. I've not gotten ZK-Snarks beyond the 5% knowledge level in all of the previous things I've read. This is the first time I feel like I've moved up the curve substantially. So thank you very much for doing this, Christian.
Yeah, thanks for saying that.
Christian, do you see a possibility to use this as a way to mix it with state channels and as a way of prevent cheating and verifications of games? So since you have the verification knowledge on chain, but you cannot really tamper with it to kind of calculate a valid result, so you can kind of predict different states that you will have certain game, and then later when people submit the results, because they cannot tamper of having information of the other participant, as a way to do the verification, but prevent cheating or prevent prediction of how to cheat. Obviously, this is top of my head, so just.
Yeah, I mean it is very flexible what you can do with this. I mean, I think I guess cheating here would be, you could possibly prevent it by hiding certain information that if the other person knew, then they had some unfair advantage. I mean, I think, so the example I gave here, you can kind of think of a more general example where you have some state in a smart contract, and the hash of the state is public, and the proof. So when someone goes in and updates the state, then the proof will prove that they followed all the rules when updating the state. And so I think that general model could potentially be used for things like games, but I haven't thought too deeply about that.
Thanks.
I have a question. I understand this for like auctions, because like it's about comparing numbers, but for a token ledger, is this really like for the lifetime of the token ledger, like not being able to see the balances, and how does a smart contract know that everything kind of balances out between all the parties?
Yeah, so that's a good question. I mean, this is kind of the downside of these types of privacy schemes, that basically the only way to know is to trust the that the verification function is correctly implemented, and that no one has this lambda 0 or lambda 1 values that would let you actually create proofs that verify, but you can put in like any hash you want. So you might, maybe you can have some kind of governance system where, like, every year or so everyone has to submit the actual balance, and then people check that the hashes match or something like that.
But can I have a limited amount of tokens, or how I know how many tokens are issued?
Yeah, that's a good question. I would imagine when, like, let's say we're just starting this token contract here, you can say that, okay, in the code of the token contract itself, you can have initial values. So you can say, okay, we're going to give Alice 10,000 tokens and Bob 5,000 tokens. And here are their hashes, but anyone can go in and see, okay, this actually says 5,000 and this actually says 10,000. So that could be the setup phase. So at that point, you know that there are only 15,000 tokens. And if you trust that that all the proofs are correct and the verification functions are working as it should, then you know that at every step, no new tokens have been created. But it's of course nicer in a way to be able to just go in and check that the way you can now. So that's the flip side here. You have to trust the moon math.
I think one thing is, like, exchanges can end up with more tokens than, like, let's say there was only 10,000 tokens issued, and an exchange could say, they can talk to each other and be like, well, there's more than 10,000 between the three exchanges. So there was already like a Zcash type clone that had that problem, I believe.
Yes, but that was a bug in the actual blockchain code.
Okay.
I think,
right. That wasn't a part of the.
Yeah, I mean, you can have an exchange trying to do fractional reserve and claiming that they have more tokens than they have. So I guess in those cases you can have, they can voluntarily publish their actual balance, and people can check that against the hash of the balance on chain. So I think that's always an option, that if people who want transparency like exchanges, they can publish their values.
Christian, the circuit that you showed us with the hash function, is that like a building block for all the circuits, is using hash functions, or are there other types of building blocks?
Yes, that is kind of a building block. So I know that one integral part of the Zcash circuit is a kind of hand optimized circuit for SHA-256. I don't have that much knowledge in how you actually create these circuits. There is a C library called libsnark, where I believe you can actually write C code, and it will like compile it into a way that you can use a circuit to generate these kinds of proving keys and verification keys. But yes, this is kind of one of the building blocks of the whole idea of shielding values by hashing them. And so this is kind of a building block in in the example that I gave as well.
I have a question going back to something we were talking about earlier. So say there are two programs that do totally different things. Practically speaking, each of those programs needs its own circuit. They need its own optimized circuit, practically speaking.
Yes.
They can use the same verifier. Do they each need their own prover?
No, so the prover, what are we doing here? So the prover uses the proving key, right? Okay. So there is kind of like a high level proving function.
So all I have to do to write my own Snark programs is just the generator. So it's easy. Great. Cool.
Yes, and even the generator is, that's kind of like a high level function. You plug in a circuit and then plug in this random lambda, and then it spits out proving keys and verification keys, and then that goes into the prover.
Sweet.
So yeah, it's I think we might see some interesting experimentation and playing around.
What type of value is the proof that is the output of the prover? Is it just a constant, or like it's like when I think of a proof, I think of an algorithm or?
Yeah, that's a good question. I don't really know. I mean, I think it's like a big blob of data, like a byte string. I don't know exactly how. I'm guessing it might be, a little bit big, which is probably part of the reason we heard that 1 million gas number. But yeah, I don't know exactly how that's going to look in Ethereum. There might be a separate data type for CTA proof. But yeah, I don't know.
Okay, cool. All right, well, that's the hour. I don't want to stop anybody from asking questions, but I don't want to keep Russell recording longer than he has to be here. And and I want to make sure that like on the hour, people feel cool to drop off. So
I do have to go, John, so I'll probably stop the recording now.
Awesome.
Okay.
It might kill the whole talk.
Oh, thank you.
Oh, yeah.
That's fine. I think we're good. We're good. Let's take it to